All right. Thanks, Ding Zhang, for a great start. And I'm going to introduce about large language model applications in healthcare. Just within this 15 minutes, I would like to first do an overview and introduce some of the applications. As many of you already seen, large language models are very powerful. Not only they can do very well on US MLE, but recent paper also shows that they can actually facilitate in informed medical consents. And also the Google AI, another kind of large language model shows the AI chatbot has better manners than human doctor, and especially on sympathetic like conversations. However, the large language models also have been reported with a lot of limitations. And then there are a lot of studies showing that these models often answer falsified results. Also, they call hallucination, sometimes even a falsification, right? And as you can see of some of these examples, it's completely made up by the model without any ground. So knowing all these pros and cons, we would like to see how we can use these models in the right application with the right context to do the right task. So what is large language model? So essentially, this all goes back to attention, which is a mechanism identified by Google researchers to enable models focus on part of the input sequence when producing output. So easily said, it's a very challenging mechanism that cost like AI researchers decades to come up with. So the basic idea is originally we have a lot of model, sequence to sequence model, try to take inputs and then to produce a sequence of output. But all these models runs into memory explosion issues or running into diminishing gradient issues because there's no focus. Looking at this particular translation example, from English to Spanish, if you want to translate like we are, actually there is a single word in Spanish. So you basically need to take the attention of the first two English words and translate to estamos, which is in the Spanish correspondence. So basically, the transformer model has been developed since 2017, and it takes many years for people to develop various kinds of variations. So from the encoder-only type of model, the BERT model, Robata, Alberta, many of these, and then the recent trend is on the decoder-only models. So it's generation. So generation with creativity, GPT models, XLNet, or these kind of models. And you can see there's actually a tree of progression on these models. Under the hood, this multi-head attention mechanism is taking all the context and then put different weights and then use these learned weights to guide the model to do the decoding so that it can achieve impressive power. And as you can see, over the time since the development of the attention mechanism, there's a lot of more methods being developed. There are two very strong branches, the encoder-only branches and then the decoder-only branches. And then the recent trend has been focusing on the GPT type of model as more and more commercial and the large-scale models are based on this kind of mechanism. With this background, I would like to give some ongoing research applications introduction so that you can see what we are doing here. So the first topic I'm going to cover is called soft prompt calibration for node summarization. As you all know, GPT models are often subject to inconsistent answers. So given one input, if you ask almost the same questions twice, you may end up with different answer. Sometimes it's accurate, sometimes it's not faithful. For example, this input, the pencil and the San Jose State practice facility and the state at the San Jose Merit, the Viking and the stock industry practice for Champos. You see, I also ask this the same summary for two prompts. The first result was accurate, and then the second one was inaccurate. And this can be a big problem if you use this for medical summary, right? A lot of like places are saying like now we can use a clinical summary tool generated by large language model to alleviate the burden. However, it have to be used very carefully, as you can see in the following example, which was generated using GPT-4. So the first summarization based on the input is aligned with the doctor's finding. So there is new pneumothorax. However, if you almost ask the same question, you ask the model to give a concise overview of the diagnosis, treatment plan, and prognosis, the answer becomes like inaccurate. And so there is an indication for pneumonia, which is not indicated in the original radiology report. So in order to address that, we come up with a novel approach called a soft prompt-based calibration. So the basic idea here is because the large language models has like a randomness, so when a prompt was given plus the input nodes, sometimes because of this randomness, it will generate output summarized result do not fully align with the input clinical nodes. So we need to rectify this condition so that we want to ensure that the output summary text always align with the input clinical nodes. How we can do that? So we introduce another soft prompt encoder. So as you know, like these models first take the inputs and then generate the embedding, and then use a decoder to generate the output, right? So at the embedding layer, we will check whether the prompt plus the input clinical nodes has a gap to the actual like embedding of the input clinical nodes. If so, then we will do an adjustment to use this soft token, which is adjusted prompt to prompt, to close the gap so that make this embedding with the prompt plus the input nodes closer to the original input nodes embedding. So close the gap, then generate a new embedding for your summarization. Using this mechanism, as you can see, now we can make our response more faithful to the input. So for this radiology report, which is about like a no radiographic evidence for pneumonia, and there's a mild pulmonary edema, and then the original summarization without our soft prompt make mistakes. But after introduce the soft prompt, all the summarization actually stay faithfully to the input. So this paper has been published in AMIA. The take-home message is we have to use these models with careful design. And if we know what we want to achieve, actually you can also achieve a similar kind of performance with the right context placed into a summarization. Okay, so the second topic I'm going to talk about is this novel method for name entity recognition without annotation, zero shot. So this is called mCodeGPT, and as many of us are doing like a name entity recognition, which is a task to extract a certain like terms or ontology confined terms from clinical report. We would like to have a magical model to generate all these outputs from unstructured nodes into a structured manner with minimum human effort, right? Traditionally, this is not an easy task because the early method either based on dictionary, rule-based, or machine learning all requires large volume of annotation, training, and even you like generated a lot of example for this model. Your generated model may not be like transferable or portable to another site if there are any structural or pattern differences. And then what we stand here is we think there is a better method to do so because large language models are actually future learners. What this means is like if you have a mechanism to guide the large language model with the right context and then give it very close examples, then the model will be able to pick up those terms without actually intensive human like intervention or training or annotation. So what are the best contextual information we can provide to this large language model in a domain-specific scenario? So we think the ontology is the perfect input for us because ontology was generated for a particular domain, and the ontology was confined into a space that is narrowed enough so that we can use that to reduce our search space and guide the model toward a confined information retrieval. So we picked this mCode, which is a minimum cancer oncology data element, as one of example, which has 100 concept with about 40 kind of relations. It's not a tree structure. As you can see, it has also relations across different entity domains. There's basically 6 big groups. So using this mechanism, we generated a hierarchy of structure, and then use this structure to guide our model to extract information. As you can see, when this model is able to detect entities in the demographics domain, like ID, name, age, ethnicity, race, then the attention on these entities will increase, which brings up the chance of finding additional unrecognized terms like email and the phone, like I introduced earlier. Because of the attention mechanism, the model knows the existence of the demographic domain, and upon identifying some of them, the model becomes even stronger in finding the rest of them. So even across different sentences, across paragraphs, the model remains strong in identifying the remaining entities. So just to show you the current experimental result, we have developed various kind of mechanism. So there's 3 different type of engines. The first is like a root to leaf streamliner. So the basic idea is I generate a gigantic prompt to connect the root to leaf for each entity, and then I ask all the results of each leaf node based on the structure, all at one time, instead of one by one. Because the correlation helps. These correlations are not random. If I ask all these questions all together, will strengthen the model's ability to recognize, also give it a much better context. However, this model is not giving us the best performance, although it's already very impressive without any training. Because sometimes, when you ask these questions, a node may not contain all the questions you are asking. So we come up with the second approach. It's called the breadth-first ontology pruner. So instead of asking all these questions to start with, we ask questions level-wise. We first ask a high level, and then go down the structure, and then expand the tree and then this graph structure until we go to the leaf node. So it gives us much better performance. The best model we obtained is called this two-phase ontology parser. So the basic idea is, and the second one is good, but sometimes if you make a mistake on a parent node, then you lose the whole branch. So now we try to ask a single question on every single node, and then try to harmonize if the existence of a path is evidenced by multiple existence of the leaf nodes. If so, then we'll keep the path. And then the first step will generate a text-specific prompt. So each text will generate its own graph structure, and we use that graph structure to generate only the relevant questions, and so that reduce the ability for the model to hallucinate. So using this method, we achieve up to 96% of accuracy using the GPT 3.5 model and even local model. So these local model trained on our GPU machines can achieve nearly 95% of accuracy. So this is very promising result. We have already put a Hugging Face web service, so interested people can go and then try out. And then we also get selected into one of the ICTR National Cancer Institute 2 demonstration page. So you can see and find our tool online. With that said, I will also introduce briefly our additional work on large language model based patient trial matching. So this is a second prize in Amy Best Student Paper Award. So we try to bridge the human, the everyday common people's language with the clinical domain language in the clinical trial, so that we can better pair the alignment and then find the patient matching the trials. And yet we came up with a novel method to come up with very complex medical condition and convert that into a mathematical proof. So this is a collaboration with a Harvard Medical School group on adverse side effect. The original input is dozens of pages of conditions and terms, and we converted that into a first order logic model and confirmed the logic with the physician. And then we convert into a mathematical proof language called Lin4. And then the whole thing becomes a mathematical proof with input of name entity recognition of a term, significantly simplify our task and improve the accuracy. With that said, I will just go very briefly and show you some large language applications I developed in School of Biomedical Informatics here. So let me show you what we are doing here.
Well, from what you've told me, Cynthia, I think the problem might be gallstones now. Did you have any worries or concerns about what it might be?
Well, not really worries. I mean, I hoped it was just indigestion. But gallstones, doesn't that mean surgery?
It could be, yeah. It's likely.
Okay. You see, we're planning this big family trip soon, and I'd hate to ruin it for them. Is there anything I could do, like diet?
Sure. You can cut down on your fat intake, since fat can provoke the attacks. At some point, they may have to be removed, though, and we don't want it to go for too long before it becomes serious. But listen, it's not an emergency now. Maybe we can work around that family vacation. So tell me, where do you plan on going and for how long?
Oh, we'll be gone for 2 weeks. We're heading down to Mexico with the whole family on a resort on the Pacific coast.
Okay, so this is for automatic speech recognition and ICD code coding at real time. A second demo I'm going to show you here is we can also use GPT models actually to digest the latest guidance and then use that to generate a quiz. So for example, I actually obtained a PDF file and then I let the GPT model acquire this information from this document and then generate questions for a short quiz. So you can see that the model is actually now retrieving, and then after it's finishing, it's actually generate a question, and then with correct answer and explanation. So the input only has the PDF document, but with this model, now we can generate a set of questions, and we already have the correct answer provisioned by the model, and also the explanation for these answers. And then so you can go over and then check the answers to see if you have the correct understanding. And after this is done, the model will grade and give a score and an explanation for the problems that was incorrectly answered. And then yet another example I'm going to show you is an interesting one for bilingual communication.
I have carefully reviewed your symptoms and medical history.
He revisado cuidadosamente sus síntomas e historial médico.
The sharp pain you're experiencing in your upper right abdomen, especially after meals, leads me to suspect that you might have gallstones.
El dolor agudo que está experimentando en el abdomen superior derecho, especialmente después de las comidas, me lleva a sospechar que puede tener cálculos biliares.
These are small, hard deposits that form in the gallbladder and can cause significant discomfort.
Estos son depósitos pequeños y duros que se forman en la vesícula biliar y pueden causar molestias significativas.
Para confirmar este diagnóstico, recomiendo una ecografía abdominal. Si efectivamente están presentes los cálculos biliares, tenemos varias opciones de tratamiento disponibles.
To confirm this diagnostic, we recommend an abdominal echographia. If you are effectively present, we have various options of disposable treatment.
Estas varían desde ciertos medicamentos para manejar la condición hasta, en casos más graves, la posibilidad de extirpar quirúrgicamente la vesícula biliar.
These were marked from certain medications to handle the condition. Even in more serious cases, the possibility of removing the biliary vesicula.
So all these three steps, transcription, translation, and the voice generation are achieved with like foundational models. So you can see like the delay is minimum, and then this kind of mechanism could help us in the real daily clinical care. And like a large language model is also beyond what you think it can do. So here's a last demo. I will show you. I'll probably speed up on this. So this is actually an app we are developing.
Hi everyone. We are presenting our stroke rehabilitation application demo. Currently it works on an iPad and will help track movement performance for home exercises.
And when you open it up, you're brought to the main screen. If you're not familiar with the exercise that you're going to be doing, you can click on the arrow to access the example videos. The example videos will have sound that will talk you through the exercise that you're supposed to do. You can also fast forward by 10 seconds or rewind by 10 seconds so that you can review the exercise. Once you are comfortable, you can go back to the main screen and press begin. You will have to grant permission for your camera to access the app. Once the app loads, you will press play.
Go down. 3, 2, 1. Start.
Based off of your movement, the app will capture the joint angle, and once a complete movement has been done,
go down.
The app will instruct you on which movement you should do next.
Go up. Go down. Go up. Go down.
The app will continue to count your repetitions. That's the number
go
that
up.
you see at the bottom left of the screen, and the time
go
is
down.
at the top left.
Yeah, so I will
Hi everyone.
not spend more time on this. And so in addition to these, we also have additional applications in drug discovery, clinical workflow automation like no-show, and survey standardization, and additional work on revenue cycle improvement. With that said, I'll conclude my talk today.